Hello everyone, Mrs. Hanson once again. Hey, look, we're on chapter 3 already, moving through our organic chemistry lessons. The focus of this chapter is on acids and bases, and a lot of this in certainly the beginning part, maybe hopefully a little bit of a review from your Gen Chem 2 days talking about acid-base theories. We'll begin the journey talking about Bronsted-Lowry acid bases, the ability to transfer a proton from an acid to a base. So we're all about conjugate pairs as we think about proton transfer in the Bronsted-Lowry conjugate acid-base theory. We'll talk about, the flow of electron density using those curved arrows. We had used something, the same thing, curved arrow notation for resonance structures. We'll now understand how to apply that same designation of an electron-rich area moving towards electron-deficient area for acid-base reactions. We'll look at a quantitative perspective of Bronsted-Lowry's. This is a Ka chart, more specifically the pKa chart. Please notice that there is a link in your e-learning that I provide you a copy of the pKa. I strongly urge you to print that just so you have it conveniently located through the lessons. We're going to refer to that quite often. And really, the more familiar you become with how it's organized and the information you can glean out of that chart, the quicker, more proficient you become. So definitely have a pKa chart. It's a link in your e-learning. It comes straight out of your text, which I also believe not only in chapter 3, but if I'm not mistaken, it might be in the front cover or the back cover of your chemistry book if you have a hard copy. That's our first lesson. We then pick up kind of in a second session, talking about more of a qualitative perspective of acidity. We'll look at the position of an equilibrium. Remember how we talk about equilibrium as a dynamic equilibrium pushing forward and reverse at the same time, and the proper choice of reagents to influence the position of equilibrium. And then we start looking at leveling effects, solvation effects, counterions, and Lewis acid-base theory, which we talk about in the Lewis theory as electron transfer. So with Bronsted-Lowry, it's all about proton tracking, and with Lewis acid-base theory, we track electrons. So let's dive in. We're going to begin with a definition, just a reminder that a Bronsted-Lowry, an acid donates a proton. And remember, a proton is simply another name for saying H+. The hydrogen ion is indeed the same thing as a proton. An atom of hydrogen, right, has one proton and one electron. It has 0 neutrons. So that loss of electron to form a positive ion leaves you with simply a proton left. So a proton is the same as saying hydrogen ion. So if an acid donates a proton, where does it go? Well, it goes to the base that accepts the proton. So a very classic example of Bronsted-Lowry acid-base chemistry gives me HCl, hydrochloric acid. Highlighted in red is the proton, HCl. And over here it's reacting with water. Now notice water has a very rich electron region on top of that oxygen. The polarity of the bonds are even bringing the electron density towards the oxygen. The polarity of this bond is bringing the electron density to the chloride, leaving the hydrogen very electron deficient. Now, the Bronsted-Lowry theory says we're going to have a proton transfer. A proton is transferred from an acid to a base. So thinking about the mechanism, this very rich area on the oxygen, water acting as a base in this example, will reach out to pluck off, remove, steal away the proton from the acid HCl. And when it does so, this bond, which is made of 2 electrons, right, a shared pair, the bond collapses on the chloride and giving it another set of dots. So on the product side, we now have the chloride ion. Notice now it has 3 sets of dot, and the formal charge is -1. Chlorine lives in group 7, but it has 8 assigned electrons. That's why it's a -1 formal charge. And since water accepted a proton, notice that the pair of dots that used to be on the oxygen is now a shared pair to that with the hydrogen. So here we have one shared pair. The oxygen itself, remember, it lives in group 6. It has 1, 2, 3, 4, 5 assigned electrons, and that's why we see the +1 on the hydronium ion. That's the acid ion in acid-base chemistry. And that +1 charge represents the formal charge on the oxygen. So with an acid-base proton transfer, we require 2 arrows to represent the reaction mechanism. The base reaching out for the proton and the bond collapsing to form the anion, which would be the conjugate base of the acid. So that's the journey in this first section, is just reminding us about Bronsted-Lowry acid-base pairing. The species that forms are known as conjugates. So a conjugate acid forms when a base accepts a proton. The conjugate base forms when the acid gives up its proton. Remember a general rule: between 2 pairs, acids always have 1 more hydrogen. So conjugates are those 2 species, one from the left side, one to the right side, that only differ by the absence or presence of a hydrogen ion. For example, this alk oxide anion, oxide, hear that O? Alk oxide means it's got a carbon group with an oxide negative ion, alk oxide anion, reacting with water. So now all of a sudden we have this very electron-rich oxygen area. And based on polarity, you know that hydrogens in a water molecule are very electron deficient. And so that deficient hydrogen is partially positive. It's a great target for this electron-rich alk oxide anion. So the mechanism in this conjugate pair, the alk oxide anion acting as the base, reaches out for the partial positive hydrogen, that's the proton, and it plucks it off of that water molecule. The shared pair of electrons in that covalent bond then collapse back onto the oxygen, and we form the conjugate acid of the alk oxide ion. Notice this now is a functional group called an alcohol. We have the OH. So instead of 3 sets of dots, we have 2 sets, and now a bond leading out to that proton, and the hydroxide conjugate base. The conjugate base of water is hydroxide. So a proton has been transferred in Bronsted-Lowry acid-base pairing. If we think about just really practicing the definitions, we start to see a pattern when we see electron-rich areas if we think about ammonia and water. Well, let's really consider that by drawing out the ammonia molecule, which has a pair of electrons on top of the nitrogen, making this region very electron-rich. Based on the polarity of the bonds, you can see that these hydrogens, the electron density is being pulled away from the hydrogen and towards the nitrogen, making these, of course, positive regions, an electron-rich nitrogen. And so when we see that it's reacting with water, and water, of course, we know also has its own polarity set up. The polarity is being pulled towards the oxygen, making this a very rich area on top of the oxygen for electrical charge, and the deficient electrical charge there on hydrogens. So knowing that opposites attract, we see a proton transfer originating from the lone pair of the nitrogen heading out towards the positive region on the water molecule. When it does so, a proton is transferred. So these shared pair in this covalent bond then collapse back onto the oxygen. And what have we formed? Well, the conjugate acid of ammonia is the polyatomic ion ammonium, NH4, and notice that the positive formal charge on nitrogen needs to be shown there, NH4 plus. And the conjugate acid that forms from water when it gains its proton would be the hydronium ion. Whoops, I did that the wrong way. We took off a proton from water, leaving its conjugate base, silly. This would be the OH with 3 sets of dots and the negative charge to represent the formal charge on hydroxide. So ammonia has turned into ammonium, and water has turned into the hydroxide ion. A proton has been transferred. Ammonia was a base. It accepted a proton, forming its conjugate acid. Water acted as an acid, forming its conjugate base, hydroxide. And any proton transfer reaction mechanism will involve 2 arrows. This, we'll learn, is a concerted mechanism, which simply means it occurs in one step. Even though I'm drawing 2 separate arrows, they're happening at the same time. With acetic acid and water, we also have a proton being transferred. Acetic acid is a carboxylic acid functional group. Carboxylic acid. And so here I can see a very rich region of electron density on this oxygen. And as a matter of fact, we can see it being pulled even further up towards that carbonyl oxygen, making the hydrogen very positive. This is the proton in this carboxylic acid that will be removed during a proton transfer. It's going to react with a water molecule, but in a different way than the base did of ammonia. So if carboxylic acid is acting as the acid, we're now looking at the other part of the molecule of water, the very rich region of the oxygen. The oxygen will reach out, like the pair of electrons are going to reach out towards the positive proton on a carboxylic acid, and it's going to remove it. It's going to pluck it off. And when it does so, the shared pair in this covalent bond collapse back onto the oxygen. And what results are conjugate pairs. The carboxylic acid, when it loses its proton, forms a conjugate base that has O negative, because now the formal charge there represents a -1. This is the conjugate base of acetic acid. This would be the polyatomic ion called acetate. And just making sure that's going. Over on the water side, because it accepted a proton, we now have the conjugate acid of hydronium. Again, oxygen with its positive formal charge makes the hydronium polyatomic ion, which is the conjugate acid when water acts as a base. So there's our theory, kind of just getting an idea of where we're heading with our acid-base chemistry. So I've been showing these curved arrows as representations of electron movement, and we use it to describe the flow of electron density. And they're very much the similar, same arrow describing resonance that we used in last chapter, but that was more of a delocalized bond, right? In other words, if I had an aromatic compound, for instance, I could use these electron arrows to show that each bond could move to a separate place. And in a resonance structure, we could simply move the delocalized electrons to the next position. That's not done by spinning, but rather it's just done by moving the carbon double bonds. And we said really that this could be represented as an equivalent structure with delocalization by just placing a circle. But notice that the arrows are being used to represent electron flow in a resonance structure. We're doing the same thing. The arrows are representing electron flow. We're using them to represent a proton transfer, which is actual chemistry, right? So I'm actually moving electrons in a reaction mechanism. They are physically movement of electrons, not a resonance structure, which is a hybrid, but an actual movement from reactants making new products. Learning to draw these electron arrows is of critical importance, every time we introduce a reaction mechanism and dive in for understanding, we're tracking electron flow. So these acid-base electron mechanisms occur in a single step, even though we have two arrows being represented. They are really thinking about this occurring simultaneously. The base attacks the acid using a pair of electrons. So this very rich region of electrons on the oxygen reaching out for the proton on our carboxylic acid. See that functional group? COOH, a carboxylic acid. This proton is then removed, causing the bond to collapse on back to the oxygen. The bond turns into a pair of dots, putting a negative charge on that oxide. The conjugate acid of hydroxide is water. And so the base has a conjugate acid. The acid has a conjugate base. Remember, the acid cannot lose its proton without the base taking it. All acid-base reactions occur simultaneously, even though there's two arrows, they occur at the same time. Now, sometimes, in a future mechanism, you might see an actual multi-step mechanism that involves multiple steps. Acid-base proton transfer is not multiple steps. It's one step with two arrows. So here represents an example of a multi-step reaction. Let's kind of go through. Let's call this, just to keep track of it, structure 1, structure 2, structure 3, structure 4. You might want to write those in your notes to kind of help track the flow of electrons. Now, here we have a polar bond looking at the very rich region on the oxygen. And this is the hydronium ion, which means based on the polarity, the electron density is being pulled towards the oxygen, making this a very deficient region of electrons. So the hydrogen is partial positive, and the oxygen region is partial negative. And we're looking at a transfer of a proton. The oxygen reaches out for the proton, and when it plucks it off, it breaks this bond. When the bond breaks, the bond collapses, and you get a pair of dots on the oxygen, which used to be the bond. This, by mechanism, is an acid-base proton transfer. So now what do we have? Well, we started with an alcohol functional group. See that alcohol? And now all of a sudden we have a protonated alcohol. Following the arrows, this bond, which is a pair of electrons, simply breaks, and it takes its electrons with it. We're saying minus water here. The H2O gets up and leaves. And I might as well introduce that. It's going to be called a leaving group. A leaving group leaves. That's what its job is. So the H2O just gets up and leaves by breaking the bond. That is not a proton transfer. When a leaving group leaves, it's a single step, but it only involves one arrow. But what's left now is a carbocation. Right here we used to have, you're looking at 3 carbons leading to an OH. Well, we still have 3 carbons, but since it's missing a bond, you see the positive charge. It only has 3 bonds instead of the 4 it requires for stability, and thus you see the positive formal charge. Now look, the end of this chain, there is 3 carbons there. Just kind of think about what that structure is representing. Each one of these terminal end carbons has 3 hydrogens attached to make sure that each has 4 bonds. The central carbon only has 3 bonds and thus a formal charge of +1. The hydrogen here, which is being highlighted, is now going to be plucked off by the water molecule that left a moment ago. So minus H2O, it's still out there, isn't it? The leaving group that just left now acts as the attacking molecule. It will be the base in the next step. The carbocation acts as an acid. The water reaches out and abstracts that hydrogen from the terminal end of the carbon, forcing this bond to collapse. When we collapse this bond, we now have two bonds, and we formed an ene, the double bond product. We've undergone acid-base proton transfer, and in doing so, we produced the alkene as our final product. All right, so all of that's really seeding the entire journey of organic chemistry. Being able to track electron flow helps us predict products by really understanding where the electrons are moving and why they're moving there. Don't worry about correctly used curved arrows to show acid-base reactions, proton transfers for now. All of the other reaction mechanisms are going to come to us. So let's keep practicing. I'm going to do some of your homework with you. So I pulled these from your skill builders. Write these out with me in your notes and you'll be that much closer to having them done for your homework. It asked us to draw a mechanism for the following acid-base reaction and then label acid-base and conjugate pairs. So the first thing I like to do is just find one on the left and one on the right, two structures that are different just by the number of hydrogens on that atom. You can see water with 2 H's and hydroxide with only 1 H. So they are the same structure that differ just by the presence or absence of a single hydrogen ion. And we know the one with more hydrogen will always act as the acid, and therefore its conjugate base must be hydroxide. Labeling the methoxide anion to methanol, which is an alcohol. The one with more hydrogen is always the acid, making methoxide act as the base. Now that you have them labeled, you realize that the arrow must always originate with the base. You point towards the acid from the electron-rich area of the base. So if the methoxide is the base, the electron-rich area is going to reach out for the positively charged hydrogen ions. And you can see that distribution of charge making hydrogen positive. So I see that reaching out for the proton when it plucks it off, the 2 electrons that are in this bond collapse back onto the oxygen. There's the second arrow, forming hydroxide, and the protonated version of methoxide turns it to an alcohol known as methanol. We had 2 arrows in a concerted mechanism, means it's really one step. Even though there's 2 arrows, they are occurring simultaneously. We could do another from our homework. Oops, that's just our answer, just to double check. We've written that correctly. Here we have phenol, which has an aromatic benzene ring attached to the alcohol group, OH. We have hydroxide. We have this oxide anion and then a water molecule. So just kind of getting our feet wet of what we're drawing. We know that even though they're not there, that oxygens all have these dots around them, and just based on what we see for formal charge, if it's a -1, it has 3 sets of dots, and if the formal charge is none, it has 2 sets of dots. So I can kind of fill those in. Hook together the conjugate pairs, those that differ only by the presence or absence of a hydrogen ion. The one with more hydrogen is always the acid. The one with less hydrogen will be its conjugate base. And between hydroxide and water, water has more hydrogen, so it will be the conjugate acid, making the hydroxide act as the base. Once you have them labeled, you know which direction to originate the arrow, in which direction to point. The arrow originates at the base. So think about this polar bond making this hydrogen very positive in terms of the electron distribution. The very rich oxide in the base here of hydroxide reaches out for this proton, and when it does so, when it removes the proton, it makes this bond collapse back onto the oxygen. Those two bonds, or the two electrons in the bond, collapse back to become a set of dots on the oxide anion. Very, very simple once you do many repetitions. Do some more homework with you. I love practicing because you're becoming proficient and speedy. Here we have a set of conjugate pairs. I like to hook together the conjugate pairs and label them, knowing that this terminal carbon actually has 3 H's there. And now obviously a negative charge, meaning that carbon is missing its third or its fourth bond there. So that is only 2 hydrogens. That's the negative there. And then I see nitrogen with a -1, so I know there's a set of dots up there. And what's happened? The one with 1 less hydrogen, and I can label those the first, having 3 H's at the terminal end of that carbon makes it an acid, as compared to only having 2 hydrogens at the terminal end. That must be its conjugate base. In these two conjugate pairs, the nitrogen in the central atom there is a pair of dots. Over here it's protonated. So the one with more hydrogen always acts as the acid. So we've hooked together conjugate pairs, remembering that we always originate the arrow in the electron-rich area, and we go to the electron-deficient proton. So the first arrow is reaching out for that terminal end hydrogen, and when it plucks it off, it forces the electron in the bond, the shared pair, collapses back on the carbon. And so you don't see it, but that's a set of dots making that a -1 formal charge. 3 bonds and a set of dots, a set of electron making it a -1 formal charge. So we have 2 arrows and conjugate pairs. Oh my, one more even. I'm really doing your homework for you. So here I have a carboxylic acid. See that? COOH, C-O-O-H, COOH. And I know there's some dots on here to finish out the valence electrons. I know that an acetic acid or any carboxylic acid will form a conjugate base when it loses a proton. These two are conjugates. And hydroxide and water are conjugate pairs. So here I start the arrow. Think about polarity. This is a very positive proton making this negative area on the oxygen electron rich. We reach out for the proton. So my first arrow kind of looked a little messy there. I'll redraw. The first arrow starts from the oxygen's dots and reaches out to the proton, forcing this bond to collapse back onto the oxygen. A concerted mechanism where a proton has been transferred, forming conjugate pairs. Whew, those are a lot of good examples. I think we've mastered Bronsted-Lowry acid base and proton transfer. Let's bring in a little numbering system, specifically the pKa chart next. So the next steps, we're going to examine how strong or how weak an acid is. Now in Gen Chem 2, you talked about strong versus weak and setting up an equilibrium. I represent the term strong as the ability to 100% ionize in an acid reaction or a basic reaction, ionize. For example, HCl is one of the 7 strong acids. That means when I place it into water, it 100% ionizes to form its aqueous ions, right? And the strength of the acid lies in the amount of ions it can produce. So a strong acid creates lots of ions. you're favoring the right side of our dissociation equation. Whereas a weak acid, let's just say, for example, acetic acid, here's the ionizing proton, because it's weak, it only partially ionizes to create its aqueous ions, that the equilibrium lies far to the left, favoring the molecular form. And remember, acid is measured by how many protons there are in water. That's the whole fundamental scale of the pH system. Strong acids give me lots of protons in water. Weak acids don't give me as many protons in water. So this represents a very weak acid favoring the left side of the arrow. As a matter of fact, about 99% of the dissociation lies to the left of that equation. So comparing the terms strong versus weak relates to the degree of ionization. How successfully can the acid dissociate to form its aqueous ions? So the strength of an acid or a base is also very helpful to predict how reactions will progress. And as we get our feet wet in learning how acids compare in terms of proton transfer, we're going to do so in two ways. Quantitatively, using numbers, a pKa chart to be specific. And then in the next section, we'll talk about it qualitatively, just comparing strength based on structure. Is the negative charge being able to be strengthened or stabilized? And so we'll, again, next chapter qualitatively. In this section, we're going to do it quantitatively. pKa charts out and ready. So when we examine Ka or pKa, it's using numerical data to compare how strong or how weak acids are. In just general chemistry, just an HA to represent any acid. And when I place it in water, it dissociates, it ionizes, it breaks apart, falls apart, dissociates into aqueous ions. Of course, this would be the conjugate base of HA, and this would be the conjugate acid of HA. The more ions we have, the stronger the acid. So that means if I compare how much do we have in terms of molar units of the aqueous ions set over the molar units of the reactants, we get an equilibrium expression. And I know you did these before in Gen Chem 2 especially, an equilibrium expression. You started your journey with equilibrium talking about Kc, the concentration, Kp, the pressure of gases. You then moved into Ka for acids, Kb for bases. You probably even spent time doing KSPs, the solubility product of salts. All of those are equilibrium expressions that simply represent the expression of the ratio of products over reactants, where those brackets stand for molarity units, which are concentration units. And it's just an expression that gives us a number. And it's the magnitude of the number, how large or how small the number is, that's of interest to a chemist. The unit itself, the K constant, has no unit. It's just a number, and the magnitude gives us great information in comparing. Well, let's suppose we have an equilibrium that's really favoring the forward direction, making a whole lot of aqueous ions. What would that do to the Ka constant? By the way, do you see how Keq incorporates the water concentration here, and the Ka eliminates the water because it's a pure liquid? Do you remember learning pure liquids and pure solids fall out of Ka expressions or Kb expressions, K expressions in general? So because it's a pure liquid, it dropped out. We get the Ka expression. If we have a strong acid, we favor the forward direction of this equilibrium. We have very high concentrations of the ions. We have big number over smaller number. And so you can see Ka is very large, bigger than 1, for strong acids. On the opposite thought plane here, let's suppose that we had a very weak acid, which means that the forward direction hardly takes off, and we're favoring the left side of the equilibrium. Equilibrium is lying to the left. And this is what it would look like for a very weak acid. Weak acids do not dissociate with much success. And so we end up with a smaller number products over a larger number reactants to give us a fraction, which is a decimal point, which means it's smaller than 1. The weaker the acid, the smaller the Ka. The stronger the acid, the larger the Ka. And we can see these Ka values having, a variety of magnitudes of number. They can range from being very, very small numbers, 1 times 10 to the negative 50. That's like 49 zeros, then a 1, right? 0.000, 49 of them. It's a very small number. Up to 10 billion, 10 times 10 raised to the 10th power. So there's such a large magnitude. And these are very small, very large numbers, which are hard to work with. So we prefer to use a pKa scale instead of just the Ka value itself. Now remember, P is just a mathematical term. It means negative log. If I have a pH, for example, I take the negative log of the hydrogen ion. If I have a pOH, I take the negative log of the hydroxide ion. That's just what P means. And so if I have a pKa, I'm just taking the negative log of the Ka value, and it comes up with a more manageable number. So instead of having numbers 10 to the negative 10 or 10 to the positive 50, those are big and quite small, you can just be looking at numbers from negative 10 to 50. That's much easier to manage. But keep in mind it's a logarithmic scale. So even a small movement of number is an incredibly large difference in value. This is an example, just a little snapshot of your pKa chart. And again, in your text and in your e-learning, I provided you one to print, and it has a much more extensive list of acids and their conjugate bases. But as you look over this table, as you read on the left column, these are acids, and they're doing a nice job even of highlighting the proton for you in red, the ionizing proton. And then over here, once it's lost its proton, it forms its conjugate base. And so the right column is its conjugate. And in the middle, you see its published pKa value. Notice that the very strongest acid listed here is sulfuric acid, H2SO4. It has a value of -9. Well, that's a very small number, indicating that it's a very strong acid because it's a pKa. So a strong acid has small pKa values. And as you progress down, here we have a protonated ketone. You see this carbonyl carbon, C double bond O, leading out to an extra proton, making the formal charge on oxygen a +1. It has a value of -7.3. Underneath that, you see hydrochloric acid, HCl. Here we have a hydronium ion, H3O, +1. Here's your carboxylic acid. See that? Carboxylic acid. This is an anhydride. This is phenol, which means that alcohol is attached to an aromatic ring. Here's just plain old water. Here we have a primary alcohol. That term primary means that that OH group is attached to a carbon that's simply attached to one other carbon. And just giving you an idea, this would be a tertiary alcohol because the carbon attached to the OH group is attached to 3 other carbons, and it has a difference in the pKa value. And again, your chart provided either from your book, from printing and e-learning, it's going to be a provided test-taking tool page. Get familiar with how to read this chart and do so quickly. The worst thing that could happen is you use your quiz minutes staring at your chart, not understanding where to find things. Now let's emphasize, for example, notice sulfuric acid is -9 and HCl is -7. On a number line, here's -7, -8, -9. As you're getting smaller and smaller down the number line, sulfuric acid lies at -9 and HCl adds at -7. Well, the difference in a number line jump is only 2 units, but remember this is a logarithmic scale. That's the power of 10. So going from -7 to -8 is 10. Going one more is, again, times 10. So from -7 to -9, that's 2 zeros. 100 times stronger sulfuric acid is in terms of its acidity as compared to HCl. Now, both are very strong, but we can see just the slightest change in number gives us an incredibly different strength of the acid. I'm going to be just a little bit sneaky and have about 5, 6 of these questions, and the redundancy I know will be there, but it's on purpose to make you use your pKa chart and really get familiar with it. So I'm going to ask you to look at 2 structures, use your pKa chart, and determine which compound is more acidic. It's not a tough question. When I ask you more acidic, I want the smaller answer. The smaller the pKa value, the stronger the acid. Now that's an easy question to answer, but you've got to go to work and find the pKa values. So first of all, find acetic acid. This is a carboxylic acid functional group. Over here we have acetone. Notice this is a ketone. The functional group is called a ketone, but we're looking at the carbon next door specifically. So the carbon in the second position from the carbonyl carbon. Can you find the pKa values of those 2 protons? Well, here I have reported. Let's see if you found the same thing. This carboxylic acid, I found the value on my pKa chart to be 4.75. Notice this is the carboxylic acid. This is its conjugate base. Then I went to work and found this structure matching the acetone and found its value is 19.2. Now that I have the answers in terms of pKa values, it's quite simple. The smaller the number, the stronger the acid. The only trip up is if you find the wrong structure or can't seem to find the what we're looking for in the chart. And just remind yourself that 19.2 minus 4.75 gives me roughly 14.5, right? And so what that means is that carboxylic acid is 10 raised to the 14th power times more acidic than acetone. Do you see? That's a really large number. It's 1 with 14 zeros after it. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Isn't that an incredibly large number? And so when we say it's more acidic, it's incredibly more acidic based on the numbering system of a logarithmic scale. The pKa chart represents zeros, just like the pH scale does. Try another. Draw these structures. Take a moment, look up their pKa's, and then identify the more acidic compound. I'll wait a minute. You do it. Pause the video. Okay, so that means you're back and you've got an answer. Let's see if it matches mine. Using my pKa chart, I found the alcohol group that's a direct attachment to the benzene ring called phenol has a value of a pKa 9.9. I then went to the pKa chart and found that for water, and it's 15.7. The stronger acid has the lower number. I'll do another one with you from your homework. Hydronium, HCl. Pause the video, Come up with an answer you can verify. Come back to me when ready. Okay, welcome back. I'm just going to say, yay, I'm celebrating with colors. All right, so here's what we found. H3O plus has a pKa of negative 1.74. HCl has a value of negative 7. The more small the number is, negative 7, makes it a stronger acid. Easy peasy. Oh my goodness, another one. You don't have no homework left. I can see this is sulfuric acid. This is the protonated ketone. Find the Kas. Come back when ready. Pause the video and come back. Are you ready? I found negative 7.3 and I found negative 9 on the pKa chart respectively. The stronger the acid, the smaller the number. Remember, negative numbers going on the number line, they get smaller as you proceed down, right? So negative 9 is a smaller number than negative 7.3. Cool, we're doing it. Super proud of you. You know what we can also use the pKa chart for is quantifying basicity. How basic a species is in comparison to another. So notice what we have here. I said we have conjugate acids written in the first column and their conjugate base written in the far column. Notice the pattern says the stronger the acid, the smaller the number, but strong acids have very weak conjugate base. Acid strength increases as you read up the left margin. The base strength increases as you go down the column. The strongest acid has the weakest conjugate base. So, really what we're asking ourselves when we say, who's the weakest base? You can just flip that and say, who is the strongest conjugate acid? And use the pKa values from there. So, for example, here I have a functional group known as an anhydride, anhydride. Notice here that there are indeed hydrogens, and therefore we have a set of electrons as well. So here's 1, 2, a set of dots, and 1 hydrogen, and that's giving that carbon a formal charge of -1. Remember, this is a base, so you're looking at the left side of the pKa chart to find it. Find the structure that matches that picture, but it's going to, did I say left? Oh, Linda, I want the right side without looking at one. I know I messed up. The left side gives you acid. The right column gives you its conjugate base. And here, of course, we see another lone pair of electrons on this carbon, giving it a minus charge. This is the carbon that's directly next door to a ketone. Go to work and find which one is the stronger base using your pKa. When I ask you the stronger base, I'm really asking you which acid is the weaker acid. Which has a conjugate acid that is weaker than the other one. So, you're using your chart. Don't cheat yourself. Find those values, and then we can compare. When you found the base on the right side, the conjugate acid on the left side, you saw a value of 9.0 for the conjugate acid. And on the other side, you found the conjugate base and acid given a 19.2. Alrighty, so those are the structures you found using your pKa chart. And what do they mean? So this tells me the stronger acid has the lowest number. The strongest pKa value, right, is the lowest number. Strong acid, weak base. The bigger pKa value meant that was a weaker acid, therefore this was the stronger base. The bigger pKa tells me that that conjugate base is stronger than the conjugate base on the other side. That's our answer. Here's some more homework practice. Identify the stronger base in each of the following cases. Use the right side of the pKa chart. Those are the conjugate pairs. The stronger base will be below, right? Because we're going this way in terms of stronger bases. Stronger base. And up here is a weaker base. So you just really want to see where they lie on the pKa chart. So which one is below the other on the pKa chart? And that's your answer. The stronger the base will be further down the column on the right side of your pKa. Here we're looking at the terminal end of an alkyne. The triple bond is the YNE functional group. The terminal hydrogen is an ionizable proton. It can act as an acid. It has a value of 25 for its pKa. And I say that the pKa is going to the conjugate acid of that base. The amide ion, the amide has a pKa published as 38. The conjugate acid is 38. Now remember, this goes to the acid, not the base. The weaker acid has a bigger number, therefore it has the stronger base. So the amide is the stronger base because it has a weaker acid. You ready for another? These are really just sneaky ways of making you practice using your pKa chart. Again, this is the INE, and this is an ANE, the alkane and alkyne terminal hydrogens. And when you look on your pKa chart, the very bottom of the bottom there is the alkane, the conjugate acid here. The alkane has a pKa of 50. And the terminal end hydrogen of the ine has a pKa of 25. So clearly you see that this is the weaker acid, and therefore its conjugate must be the stronger base. We getting it? Oh yeah. Oh, another one. Now look at, these are bases. So don't fall for it. Look on the left side. The bases are on the right side of your Ka chart. The right side on the pKa chart. Go to work and find their conjugate acids, pKa, and we'll compare. This protonated ketone has a pKa of negative 7.3. That's the conjugate acid of this base. This is a water molecule. Its conjugate acid is hydronium. The hydronium has a value of negative 1.74. So this is the weaker acid. Therefore, this is the stronger base. I'm going to emphasize the skill again. If you're reading down, this is the conjugate base side, you know that the conjugate acids increase as you go up the column. The conjugate base strength increases as you go down. So if you're asked for the strongest base, compare their locations. It could be that easy. You want the one at the lower end. So when we said water was a stronger base, that means it's lying below the ketone on that conjugate base side. So all I have to do is find the one that's more toward the bottom to find the stronger base. To find the stronger acid, find the one highest up on the left side in comparison. We can also use a Ka value, and this is kind of the last skill for our lesson today, using a Ka value to predict the equilibrium, which side of the equilibrium is going to be favored. So Ka values that are used to predict if the left side of the equilibrium is being dominant or is it the right side that's being dominant. And it really is as easy as identifying the strong acid compared to the weak acid in conjugate pairs. So for example, we have a Bronsted-Lowry acid-base proton transfer. Let's kind of just bring in the chemistry here of what's happening. We have a base that's very electron rich on that oxygen. The water molecule, we know based on polarity, is electron deficient, so it's positive on this hydrogen. We see that the hydrogen is being abstracted, plucked off, removed, transferred from the acid to the base, forcing this bond to collapse, and we've formed conjugate pairs. The arrow originated at the base, and it formed its conjugate acid. Water acted as the acid and formed its conjugate base. Once you label the conjugate pairs, I want you to identify the two acids. One will be on the left, the other will be on the right. Identify the two acids. And when you do that, I want you to then find their pKa values. On the pKa chart, the published value of water is 15.7. On the pKa chart, the published value of pKa for a tertiary alcohol. Tertiary means that carbon attached to the alcohol functional group is attached to 3 other carbons. And it has a published pKa value of 18. Which one is the stronger acid? Well, the stronger acid has the smaller pKa. It's up higher on the chart. And always, 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 the equilibrium will favor the weaker side. The larger pKa indicates that this is the weaker acid compared to the one on the left. So you can see the equilibrium pushes or favors the right side of the dynamic equilibrium. The equilibrium will always favor the weaker acid and the weaker base. Identify the two acids and compare their Ka values. So for example, another example, we have a water molecule acting as an acid. The conjugate acid that forms from the base is a straight chain alkane. The base accepted a proton to form its conjugate acid. The acid donated a proton to form its conjugate base. When you identify the two conjugate pairs, those that only differ by the presence or absence of a hydrogen, identify the two acids and look up their Kas. The larger the Ka, the weaker the acid. And you can clearly see this reaction would be pushing in the forward direction. So much so, the magnitude is so different. A 15.7 compared to a 50. And if you subtract that, you get about 34. Well, that's 1 with 34 zeros after it. That's a really big number. So that really means that there's not much success at all in heading back to the left side of the equilibrium. Not much of an equilibrium. It's more like an irreversible reaction because the magnitude of the different pKa values is so significantly large. Here's some homework problems for you, and I really should have started with having them covered. And it's going to ask you to determine the position of the equilibrium. Now, the secret lies in finding the Kas. So I said step 1 is locate the acids, right? Find the conjugate pairs and label who's acting as an acid. Find the acids. One will be on the left, one will be on the right. Between this ketone and this protonated ketone, those are called conjugate pairs. The one with more hydrogen will act as the acid. Between hydronium and water, hydronium has more protons, and therefore it acts as the acid. We want to just locate one on each side who are the acids in this dynamic equilibrium. And once you locate them, tell me their pKa values. What are they? And that's where I need the chart. And so I went to the pKa chart and I found hydronium, and it has a published pKa value of negative 1.74. The protonated ketone has a published pKa of negative 7.3. Determine the position of the equilibrium says, equilibrium favors the weaker side. The weaker acid has the larger number. Negative 1.74 is a bigger number. So you can see the dynamic equilibrium is favoring the left side of the equation. This is the weaker side. This must be the stronger acid side. We favor the weaker side in the position of the equilibrium. Here's your other homework question in this section. Here we have a anhydride. It's a functional group. 2 carbonyl carbons separated by a carbon there. And then all of a sudden, remember, this would have 2 hydrogens. A proton has been abstracted. So you can see the mechanism says these electrons rich on the hydroxide are reaching out to abstract that proton. When it does so, that bond collapses and you see the negative charge on that carbon. We have a carb anion form. Because it has 5 assigned electrons, we see a formal charge of negative 1. Remember, the hydrogen's still there, one of the 2 hydrogens. And the other one went over here, we had a proton transfer. So here, these 2 are conjugate pairs. This is the more protonated. It has more hydrogen on it compared to hydroxide, so it's acting as the acid. Here are 2 conjugate pairs. The one with more hydrogens, notice this has 2 hydrogens, whereas this only has the 1. This must be acting as the acid. Find the pKa values for the acids we just highlighted. Going to your chart, we see water has a published pKa of 15.7, and the anhydride has a published Ka of 9.0. The larger number is the weaker acid, meaning the equilibrium is favoring the formation of the weaker acid. So this equilibrium is lying on the right side, favoring the forward direction in the dynamic process. Favors the weaker side. And we're going to stop our video here. This is a lot of work we've done. Good work, team. We've got the first 3 of our 9 sections of Chapter 3. The next lesson, I'd like to group 4, 5, 6. In video 3, we'll group 7, 8, 9, bring closure. So that's my goal anyway. Good work today. Take a process break. I'm going to need one too.